I recently conducted an IOI preparation programming camp for Kazakhstan team via the internet, and I was allowed to record everything and share it later on YouTube, so in the next few days I will post some of it here. The video you're watching right now is problem analysis of Innopolis Open 2018-2019 that has quite hard problems. I strongly recommend that you first try to solve everything yourself and then go back here to see solutions. There should be timestamps in the pinned comment below, so you can just jump to a particular problem. That's it, enjoy the video. We have some money, say M, and there are two options that we have, each described by L1, let's say low, high, and percent of what we gained from that investment. We can use this option by spending money between low and high and getting interest P back. And second thing as well, low 2, high 2, and P2. In problems like this, we often should, I think that's also true for a lot of geometry problems, we should see that only some extreme cases, extreme scenarios make sense. If low and high is some interval that we can spend, and low 2, high 2 is also some interval, then it doesn't make sense to spend some money here and some money here. It's better to move the money that we invest so that, because one of those two options will have bigger interest. Even if they are equal, it's still okay to move one of them, and to say that if there is a tie, we maximize the second thing, and we can move what we spend till we hit something. So here, from this scenario with blue points, I would move to this one, and those squares are a better solution. The same could be used for a lot of options. Let's say there are k options given to us. In each we spend between low and high money and we get some interest. Then for sure you can, for every pair, if the amount of money you spend for each of them, if it's not one of extreme points, the lower bound or upper bound of money you can invest for this one, then you can move it around to make situation better or not worse. And if I'm not mistaken, we could also solve it for k options, where we iterate over, for each option we decide whether we use it, and if yes, then whether we use low or high, exactly low or exactly high. So it looks like, I think, O of 3 to k times some polynomial, and only one option will have value that is between low and high, because if there are two things where we spend some money in the middle, we can move it around to make situation not worse and to make one of them to be the extreme value. So in this complexity we could solve the general case. Iterate for every interval whether you use the low, the high, or not use it at all. And iterate also over interval where you will have some money in the middle. There will be only one such interval. And using other values, we will compute what you spent on that last remaining interval where you spent money in the middle. So the problem could be harder. Plus, I strongly recommend doing here everything on integers. If you don't have to, don't use real values. How do we find point in the middle for k-dimensional case? Well, you just subtract, right? When you have some interval with 5 and 7, the other with 8, 10, 4, 16, 7, 8. You iterate for each interval, you decide whether you use the lower value or the upper value, or maybe don't use it at all. And for one remaining interval, you will know that here I want to spend something in the middle. Let's say that here I have 18, and the total money I have is 29. Then you add those values that you chose. 5 plus 16 is already 21. So the remaining money you have for that last option is 29 minus 21, what means Here you need to use 8. Cake tasting was about subsets. There are some shops, and we immediately will make the first simplification. If the problem tells us something about things that appear or not appear, you can always reverse what it means. If you need to count, let's say you're given a sequence and you need to count intervals that satisfy some condition, you can instead count intervals that do not satisfy the condition and then subtract something to print the answer. Stuff like that often makes the problem easier, and we will do that here. For each subset we were given what the number of different types of cakes. Yeah, there are some shops, each offers some types of cakes. For each subset we know what is the number of different types of cakes that appears in this subset of shops. This is B. Cake tasting. And yeah, we will move that first like switch, that instead of saying, let's say shop A has types 1, 2, 3, shop B has types 1 and 4, shop C has types 4 and 5. Then the numbers we would get are in shop A 3 different types, in shop B 2 different types, C 2 different types, A, B 1, 2, 3 and 4, there are 4 different types, AC, AC we have 5, BC we have 3, and ABC is 5. And this is, let's call this value, how should we call it, S, the number of, the total number of types of cakes. For the whole, if we take the number of different types of cakes for all the shops together, A, B and C, then this is the number of cakes that we operate with. And because caring about the sum of sets, so how many different things are in those sets in total, this is harder than caring about the intersection. So instead, I will, for every shop, I want to wonder what cakes aren't there. So for A, cakes that aren't there are 4 and 5. For B, 2, 3 and 5. For C, 1, 2, 3. And now for that, if I record what is the intersection, which is the opposite of sum of sets, is the intersection of the complements. There is a very important formula. A sum B complement is equal to the complement of intersection. So the sum represents items that are in at least one of them. Complement represents those items that are not in at least one of them. And one moment, here something is wrong for sure. So those represent things that aren't in neither. Here we have, I lacked this thing. So A prime means things that aren't in A, B prime means things that aren't in B, intersection is things that aren't in A and aren't in B. So like that. This contains things that aren't in A and aren't in B, and the opposite of that is there are at least in one of them. So this is the formula that we use. And from that we know that if the size of that is x, then the size of this is s minus x. S is usually called omega, but s is our number of different things that we operate with. And this means the sizes of here intersections of those complements, this is a prime, b prime, c prime, will be opposite to the sizes of sums. Here the intersection of a prime and b prime is 1. There is only element 5. Here the opposite is 1. The intersection of a and c should be 0. The intersection of here b and c prime is 2 and 3. There are 2 elements. So generally here we see the formula from here that if something had size x, then the complement of intersection of complements has size s minus that. This means we can transform the input easily with just one line per everything. Every number x in the input we change to s minus x. Now for every 2 shops we know the intersection of things that aren't there, and we will just try to figure out what are those things that aren't here for every shop. At the end we need to reverse it back to get the answer. So all this thing was to now think about intersections, and that is easier. What we need to do here is something similar to sum over subset, also called SOS. SOS. SOS is sum over subset. And there is a nice way to think about it, in my opinion. All of you should be able to solve the following problem. Given a grid, answer queries for the number of the sum of elements in some subarray, or maybe just in those quarters, like for some cell, tell me the number of the total sum of things that are to the left and up. And one way to do that is when we compute every next element, so things we want to compute for some cell, this area, then from already used like prefix sums, we can say that we take this area plus that one, so those two with pluses, and minus the red one here because we computed it twice. This is with minus. That's very easy, but we need subtraction, and it gets harder. What if, for example, we are interested in something that isn't that easy to subtract, maybe products. So what if for every cell you want to compute the product of everything that is there? Then it's harder to divide. Still you can try not to multiply by zeros if we need to do something modulo, but it's not so convenient. Instead, the technique that also will be used in sum over subset is to iterate over dimension and do something separately for every dimension. So instead of for this cell to say that we take the answer for this cell plus this cell minus this one, this is what we did so far. Instead we will just go through the grid once, and for every cell compute the prefix sum in this dimension up to this one. So we go in this direction. Just let's say dp of ij is the cell here plus the one above. In linear time, iterating over the grid, we can for every cell compute the sum in this column up to this position. After we did that, we can do the same in the other dimension. And if here we store the sum of those elements, here we store values of those elements, and so on, then now if we apply the same thing in the other dimension, going from left to right in every row, then, for example, here we will take the sum of those already computed elements. So this cell will contain the sum from this prefix submatrix. And this is what sum over subset does in more dimensions. The same thing we could apply if there were 3 dimensions. If there is, let's say, a cube, and for every cell you want to take the sum over of everything that has coordinates not greater than that. So things that are to the left, below, and the third dimension. And you also can do it for n dimensions. In complexity, for each of dimensions, you iterate over the size of that grid or whatever. Actually, this is in n dimensions not a grid, it's some hypercube. But this is, let's say, O of n times the size of everything. Where n is the number of dimensions. Of course, for 2 dimensions, this is just 2 times the size of grid. This is how many times we iterate over the grid. And sum over subset does that for n dimensions. That is, if we know for every, let's say that n is equal to 3, for every submask of size n, we have some number. Let's say here we have 7, 0, 0, 1, we have 4, 0, 1, 0, we have 20, 0, 1, 1, we have something, and so on. And now for every mask, let's say for 0, 1, 1, I want to take the sum over all the submasks. So in this case, it would be sum of those 4 values. Not to do it in 4 to the n or 3 to the n. 3 to the n, we were talking about it yesterday, is when you just iterate over submasks. The complexity is amortized 3 to n. Instead, we can imagine that this whole thing represents n-dimensional cube, where every size is, it's 2 by 2 by 2 by 2 by 2, where every bit represents coordinate in one of dimensions, and just apply this sum over subset. So the solution is for I, that is dimension, from 0 to n minus 1, for mask, every mask, what you do is you need to, like, let's say for this thing, you want to take the sum from the previous one. So you do something like dp of m plus equal dp of m XOR 1 shifted by I. Assuming that m has the ith bit on. Then, for example, if we have mask like that and I is here, then you want to take the sum from dp of this mask. This way, for a cell, you take the sum from the previous cell in this dimension. So this for loop is only over m that has the ith bit on. This is the whole sum over subset implementation. And we just need to apply that here, because what happens, let's get back to the previous slide, when we have those intersections, so we know that, let's work with example here, the intersection of, okay, so for A prime itself we had 2, 3, and 3. Using those values, 2, 3, 3, and so on, the blue ones on the right, we need to figure out what products exactly are in which shops. And we have those masks for, so A is just 1, 0, 0. B is 0, 1, 0, C is 0, 0, 1, then we have AB, AC, and BC, 1, 1, 1. We have some values, also for 0, 0, 0. We have some values, let's put them here, 0, 2, 3, 3, 1, 0, 2. And the intersection of everything is 0. If I draw edges between masks such that one is in the next layer and is the submask, I mean is over mask, like that, then actually you might recognize some pattern here. Maybe I will draw it again a bit differently. I will draw the edges again. So we have situation like that, plus there is, let's say, one more thing hidden behind. This is a cube, because we actually work with two-dimensional cube, and you can see it here in the drawing. This is the top side, this is the left front side, and this is the, oh, I liked an edge here. And this is just a cube. And what happens is that we iterate over dimension, and in each dimension we take that sum, to take the sum over elements. Then in the other dimension, in the other, here actually what we need to do is subtract. Because the goal is for every subset, let's say for subset 1, 1, 0, so representing shops A and B, we want to know how many products there are that appear exactly in those shops and in nowhere else. Let's put all of that with green. What we want to do is, so we know the answers that we should get. That is, there is exactly one product that is only in shops A and B. Now we are talking about the complements. So there is one product that is both in A prime and B prime. So for 1, 1, 0 we should get that there is one product there. From this we will be able to print something. There are also two products that are in B and C. Okay, this was a very bad example because we subtract nothing. Oh, but this will be better. For 1, 0, 0, we should get that there is one product that is unique here, the 4. While right now the value for 1, 0, 0 here is 2. But what happens is we subtract those that are in bigger things. So 2 we want to subtract with 1 and 0. And what happens, we run the sum over subset implementation, which is just here the loop from below, but with subtraction, not addition. We don't want to find sum over subset, we just want to subtract those products that are in other shops as well, in our subset and bigger subsets. So here, when we iterate over this dimension, which is the second bit, at this moment we will subtract 2 will be subtracted by 1, so it will become 1 itself. Yeah, the alternative way here to think about it is that in this cube where you have submask and somewhere there is 0, 0, 0, somewhere there's 1, 1, 1. You should think for every position what you want to get. What do you want to compute? The sum over everything that is a submask, the overmask. What do you want to do? And from this you will get the order. So because here for a subset like 1, 0, 0 for a mask, We want to subtract those masks that are our over masks that contain our bits and something more, because we know there is a product that is in shops A and B. So we don't care about it here in mask for product A itself. We want to, in 100, we want to get the number of elements that are only in the first shop, not in first and second, because using that we'll be able to print the answer. So we do that, but here we'll have minus. This will be minus equal, and we iterate only over m that here do not contain a 1, because we want to say that we do dp of that mask minus equal dp of this mask. Now's the time for questions. And the complexity will be 2 to n times polynomial, which is fast enough, and the implementation will be not more than maybe 10 lines, plus retrieving the answer. Now we will say what is the solution for C, and after we are done with all the problems, we'll get back to how to implement it. In problem C, there is a polygon given, and every query is 1 point, for which we need to decide. So actually, this is not what the statement exactly says, but this is what the solution must be about. If we draw, maybe I will do it with pencil. If we draw all the, how they're called, diagonals in the polygon, they will in some way limit our point. Maybe I didn't draw everything, but here we have a polygon that limits our point, and inside that polygon we need to find the furthest point from the given one. In this case, the solution would be this point. We should print the distance between the given point and that furthest point that is inside the area limited by diagonals. We can take a look at here the drawing. We have some polygon, and for this point x that is given as a query, diagonals create this 5 sides polygon, and the circle shows that furthest point from the given one that is still inside the same area. That's the problem, and we want to do it linearly of the number of points in the polygon. I mean, we want to answer a query in linear complexity. Okay, and the problem is easy for those who are very experienced with geometry. Then it almost doesn't require thinking, because what happens is one approach is, for the given point, every diagonal gives us the limit that, let's focus on this diagonal indeed, that everything must be on the point that will be that furthest point must be on this side. Maybe now the drawing is a bit hard to understand, so let's make a new one. If the point is here, then the fact that we have the blue diagonal means that our furthest point for sure must be on this side, somewhere on this one, or in the other, think it the other way. This area is forbidden. I can say that this line is forever, and just everything here is forbidden. I can do that for every diagonal. This is forbidden, and also here this will be forbidden, and this will be forbidden. taken out of context, this would be a strange drawing. I drew a pentagon with some red outside, and we have our area inside. And in geometry, the thing that we find, this area inside, is called half planes intersection. This is half. Let me check. Half planes intersection. Every diagonal gave us the side of the plane that is allowed. Everything here is okay, we say. And we need to find the intersection of all those allowed areas. Or here, this side is allowed. Do I show it in good direction? No, I don't, because the image is mirrored. The camera mirrors myself. So for you, it's this side. Yeah, this one. And half planes intersection is a bit scary, but it's very similar to convex hull. The idea is that just like for convex hull, you want to find, let's say for those few points, you want to say that, oh, this point doesn't matter because this is convex hull and this point should be skipped. So it's a bit similar for half planes intersection. If you have half plane like that, let's say half plane like that, and like that, then this one doesn't matter. You are looking for something like the opposite of convex hull, something that is here inside. This area is right now the intersection of everything, and that line that is pointed by blue arrow should be skipped. And the goal is, the idea is to sort lines by the slope, process them in this order, remove unnecessary lines, and then every two next consecutive half planes in our half planes intersection will give us a point. I mean, they create two consecutive sides of that polygon that is our interesting area. And then for given query of some point inside, we will just consider every point here. Why for some area that we have, why for this point we should only consider those vertices of a polygon? Why won't there be vertex that is furthest that is not the vertex of a polygon? Because if you draw here a segment that is a line that is perpendicular to here, this is right angle to the side, then going in those two directions, to the left or to the right, you will get point that is further and further away. Even if you have a segment where the point given in query is here, then still you could draw a perpendicular segment, and from this you get, if I go to the left on this segment, I get point that is further and further away. So this one will be better than anything on the segment. Like similar thing with inside the polygon. This is how you prove it. Two remaining things are how to do all of that quickly and what is the algorithm, the exact algorithm for half planes intersection. The latter we will do after we talk about all 5 problems, A, B, C, D, E. And the former we will cover now. So the thing is, given a point, I don't want to process all the n square diagonals. because that would be n squared per query. Instead, I will notice that only few of them are important. That is, if I look from this point, then I can skip this diagonal and say that the point that I'm looking for, the furthest one from the given one, must be below this line, because this diagonal limits me more. Also from below, this diagonal is the most important, and generally, for even a very, very big polygon and some given point, from every point you will have just two diagonals that are important. And you can skip all other ones, because those will not affect your area limited by diagonals. So some idea from this is, for every point, use binary search to find those. So for some prefix of points, if you draw a diagonal, the point will be on the right. What means, looking from this point A, you're looking for point B, and then you check if you draw a vector from A to B. You can use cross product to check if the point from the input P is on the right or on the left. If on the right, then move your binary search more to the right. For that, it's also helpful because we have points numbered from 0 to n-1 in a circle, like point 0, 1, 2, 3, 4, 5, 6. For a point 3, it's hard to binary search in two separate intervals, suffix and prefix. Then it's good to repeat everything. And then for point 3, what you do is you binary search in this interval. You here binary search the first point, B, such that looking from third point to that one, let's say from point 3 to point 6, and assuming that things are sorted clockwise. I don't know how it is in this problem, but there is some direction, either clockwise or counterclockwise. Then you're looking for the first point such that, let's say, the given point in the input is on the left. You use cross product to check that. So one thing, you can use binary search. In log, for every point you will find those two important diagonals, up to this point 6 and up to the next one, or the previous one. But also, instead of binary search, we can use two pointers, and that's better. It's faster. We use two pointers, and that is, again, just for any big polygon, if the point is here, if for this point I see that this is the last diagonal that is on the left from the point, then for the next point it will be diagonal to the same point, or maybe the next one, something like this. When we move this first point A in this direction, then the point B, that will be that optimum, the other point, will move also like that, just like two pointers or caterpillar. And you don't even need the connecting A with B plus 1, because for the given point, you limit it, for every point, you limit it as far as you can from the above. And when you move A, you will do the whole 360 over the point. We can analyze the example. Let's say what happens here. Say that this is first point A. Then optimal above point B will be here. I consider that diagonal because the next one would be already on the other side. And by above, I mean point is to the right from vector AB. Then from this point, this was B a moment ago. Then this is still above. So point is to the right from vector. This is still above. Then the next one is not. So this is the optimal limit. So this is A1, B1. This is A2, B2. Then I move A here. This will be the optimal one. From A here I have this one. For A here I have this one as well. And this will be anyway later skipped in half-planes intersection. And for A here I will have that one. And that optimal point B, it moves also. This was, I think it was here, B1, B2. I think B3 was here, then here twice. Yeah, after that you got those O of n half-planes. You need to implement half-planes intersection and you will get this area. This area might have size that is much smaller than n. I think we saw an example of that in the previous drawing. Yeah, here we saw that we had 6 points and the area was a triangle. Half-planes intersection of n points can be even just 3 lines, just like convex hull of n points can be just 3 points. So now's the time for questions about the algorithm. We already have O of n for 2 pointers plus half-planes intersection, and this can be done, usually it's done in n log n, because also we start just like in convex hull, but the 2 pointers technique already gave us lines sorted by slope, so actually this thing will be O of n as well. So the whole algorithm is O of n, because lines produced by half-planes by 2 pointers are sorted. Then convex hull, or here half-planes intersection, can be found linearly. And the problem was you're given 2 sets of points in 3 dimensions, but I will make most of drawings in 2 dimensions. And you need to shift one set so that it would, let's say, dominate the other set. So it's possible that I mess up what needs to be shifted, but it's a symmetrical thing. So I will assume that every B, there are points, there are, let's say, white points and blue points. Does it make sense? There are white points A, blue points B, and you need to shift every point, the whole set of A, by some vector that is like, it should be x to the right and x up. So you move by vector 1, 1. Do you see the pencil correctly? Or should I change the color? And after the shift, every point from B should be dominated. And dominated means that there is at least one point that has every one point from A that is somewhere here in this area, where each coordinate is bigger than coordinate from B. Here, point B is dominated. Could you change the color, please? Okay, so I guess the pencil one is bad. What did I have there? So we move by vector t, comma t. In 3 dimensions, it's of course t, t, t. So we move like that. We want to find the smallest t, such that after shifting A like that, every point from B will be dominated. Maybe the statement was a bit different, like maybe we shift the other set, maybe it's A that should be dominated, but all of that is like symmetrical or isomorphic. And when you need to do something by the smallest possible value and you need to find that, it's correct to say that first idea is binary search, obviously. Binary search. And then, so you binary search by t, you have already from that log of answer. in the complexity times, after you shift it, in 2 dimensions, now you would need to check for every b whether some point from A is there on the right. For sure, a good idea for that is a sweep line that moves from right to left. And then once we meet point from B, because maybe let's make a new drawing where we already shifted points from A. There are some points B, and there are some points A, and once the sweep line goes, it reaches point from B, we need to check if above this y coordinate there was already some point from A. Then it means that point B is covered. And then just one variable is enough when we sweep from right to left. The maximum coordinate y of point A so far. That's something easy. So here we know going from right to left, if we already met those points, I want to say, okay, this is the highest point from A that I met so far. If there in a moment I will meet here point B, then I say, nah, this point B is not dominated. In binary search I need bigger shift of points from A. And if B is here, everything is okay, I should continue. Yep, in 3 dimensions it's a bit harder because we have every point has one more value z. This point, so this one has value z as well. Maybe let's start with examples. You can try imagining that in 3 dimensions, but maybe it's easier to draw 2-dimensional points and say that each of them also has a value 3, 7, 8, 1 that represents the last dimension. And when we move with sweep line from right to left, and now we have point B that is here, we want to know if somewhere above this y coordinate, somewhere above here, also this B has some value z. Let's say that z is 5. Then we want to know if in this area there was point A that had value bigger than 5. For that, you can use segment tree. Segment tree built over values, like segment tree is built over this y values, so something like that. And it is able to say, in some interval of values y, what is the biggest values of z. With sweep line we got rid of one coordinate x, and with segment tree value y tells us where we should put it in segment tree, and the values that we store in segment trees are values z. Segment tree has complexity log, and we use segment tree for each of n points. The complexity is n times log n times log a, where a can be up to, I think, 10 to 18 in the last subtask. So this logarithm is quite big. It's 60 times n times log of n, which is 20. It's too high for limits. I think n was up to 500,000. The time limit would have to be huge to make log square with, especially if one log is 10 to 18, to make this work. The intended complexity is different. It's beautiful, but it's also very hard to get. Any questions at this moment? So for this 70-point solution. We want to now avoid binary search at all. What seems like a bad idea. I would go in binary search direction for sure during the contest, but there is a faster solution without binary search. And in a lot of problems, what is very important is just to try with some observations. Maybe, for example, what can we say? When we move with that sweep line and we see that we had point B and it wasn't dominated, then maybe if we see points A that are below, like here, we know, but by what value, what extra value we need to shift this point to make B dominated. We would need to consider those points, and also maybe something on the left, something is here, that if you shift by extra this distance, then point B will be dominated. And maybe then you would just continue sweep line without repeating everything. Then binary search is not necessary. That being said, sweep line relies on coordinates, so it does need the shift already. It isn't that easy. But in 2 dimensions, if there is a point B, then it's either already dominated, that is, there is a point A here, or along all the other points A, you want to find the one that is closest. What does it mean that it's closest? I'm now focusing on 2 dimensions. For this point A, the value by which I need to shift A is mean of b dot x minus a dot x and b dot y minus a dot y. This is the value by which I need to shift to make A to be at least on the level of B or above. The other is the same for X. Plus I can say that I'm interested in max of that with 0, because if point A is here, then I don't care. But let's skip that. Let's not think about it for now. And it's hard to speed up everything that has like those conditions. Here we need to compare the difference of x's and difference of y's to be able to say what is the value for point A. Shouldn't it be max? Oh, right, you're right. It should be max. Thank you. It is max of, so I will put 0 here. 0 and differences of coordinates. And what we need, I will shift that a bit to the right. What we need in the whole problem is the minimum over all points A of that. For every point B, I want to find by what value I need to shift values of A. So this chooses the nearest of points A. And this is the distance between B and A. By what value I need to shift this point A to make B dominated. If I compute this value for every point B, I will know the answer. And as I said, it's hard to work with something that has ifs. Here, the maximum is either this difference of x's will be bigger, difference of y's will be bigger, but we can visualize that maximum. The thing is, if I split the plane here, all the points that are below the green line, for them only the difference of y's matters. For all the points that are below, that are above the green line, only the difference of x matters. So I can say that the answer for B, the value by which I need to shift A, is from all these points, I need to find, actually I need to find just Bx minus the rightmost point. this value. For this area, I need to find by minus max of AY. And also check if something is here. Anything? If yes, then I'm done already. The left thing is the minimum value by which I can shift one of those points on the left to make B dominated. And here I don't have any ifs at all. I just want the rightmost point. For the area below, I have similar thing. Just choose the the topmost vertex, topmost point, A, and that's it. The solution for 2 dimensions, because of that, can be just I will use a sweep line that is not usual now, because I want to split points into those that are above some line like that and below that. For you it's like that, above and below this line. And because of that, I will sweep with this line. I have the points. Also those blue ones, B. I sweep with this line in like that, so it moves, slowly moves in this order. And when there is a point B, I ask, was there already some point? So let's forget about this part with anything. So we need to in some way separately check if B is already dominated, but if that's done, then I know that there will be no points that dominate B, and I just want so I don't even care about this line in that way. Among points that were already processed by the sweep line, I want the maximum of X. And from points that are not yet processed, I can store that in a separate segment tree from which I remove stuff, or I can do separate sweep line from right to left. So I want also from that, I want the maximum Y, max of values Y, and here max of X's. And those will be 2 candidates. I will find closest point here, A, and closest point here, A. And for each of them, I know by how much I need to shift. And I will choose the better one out of the 2. It turns out we can do the same thing in 3 dimensions. Before we do that, do you understand what happens in 2 dimensions? For point B, I wanted to simplify this, let's say, complicated formula of distance by which I need to shift point A to make it dominate point B. I split A into 2 groups, such that from this group I'm only interested in delta X, or just in the rightmost point A, and in the other group the topmost point Y. The topmost point A, which means the one with biggest value of Y. And now, how does it look like in 3 dimensions? Oh. I will try drawing that. I'm not sure if I will succeed. This is, let's say, X, Y. This is one plane, and the height Z. So what happens? What happens for point B? That is, let's say, here. then everything that has big coordinates, like all coordinates are positive, this like quarter of the whole what is it called, the three-dimensional plane. One moment. Space. I forgot the word space. So this quarter of space already would dominate B. And if I draw a line that goes in vector -1, -1, -1, -1, -1, so it goes like that. What I have something like that. I'm trying to, let's say this quarter looks in some direction, and now make a line that grows out of this quarter and just gets further away from this quarter. If I had a cube, then we're talking about, I think, if this is diagonal of this cube. If you put it further, then this is the line we're talking about. The line that goes with vector -1, -1, -1. And that line splits the space. We should split the space into three parts. Parts for which, for one part, the x coordinate matters, for the other y coordinate matters, and z. It was a bit easier in 2 dimensions, also because then we can draw stuff. Yeah, so one approach is what I did here. So try to imagine what areas we have, and maybe it would be good to make that to make some examples. If point B is just 0, 0, 0, then you can figure out for every point what matters. If there is a point -5, -2, 7, maybe let's say 3, then coordinate x matters. We need to shift this point by 5. So this belongs to the first part, the part for which we want point with biggest x. So the first part is those where x is minimum coordinate, that's it, like compared to b. Here we had the same thing. The description of this part is points that have x smaller than y. Assuming that b is 0, 0, 0. Here one part will be points where such points x, y, z, that x is smaller than y and smaller than z. Or smaller equal is also fine. For ties you can say that this point is in whichever part. Like if there is a point -5, -5 and -2, it doesn't matter if you say you need to shift by x or you need to shift by y, whatever. Still, we assume that point B is 0, 0, 0. In fact, what we care is that bx minus ax is smaller than by minus ay. This is condition that says x coordinate is more important than y coordinate. And bx minus ax smaller than bz minus az. We cannot sweep over just some condition, but we can sweep after we compute some value by which we should sort every point. And we can get that from those inequations, because the first one transforms into bx minus by smaller than ax minus ay. And also the second one, so this was the set of inequalities, the second one is bx minus bz smaller than ax minus az. If I define new coordinate x prime as x minus y, maybe let's call it y prime, is x minus y, new coordinate z prime to be x minus z, then I'm looking for points. I'm looking for such points A that A dot y prime is bigger than B dot y prime, and A dot z prime is bigger than B dot z prime. After I just replaced every coordinate like that, like y changes to y prime, z changes to z prime, according to those equations. And this is something that is much easier because this is just like two-dimensional thing. For every point, we have its y prime and z prime coordinate, and we are interested in points A such that both coordinates are bigger than those in B. So when we draw a new drawing, y prime and z prime of these new coordinates, I have some points A, and so on. I have some points B. Remember, this drawing it isn't even similar to the previous one. We just compute new coordinates. Then, because I want y prime and z prime to be bigger than that of B, for every B, I want among those points the best one. Those are points A that they are in the first of three parts. Those are in part where those two inequalities are satisfied, which means x coordinate is the most important one. In the previous drawing, we had two parts, 1 and 2. And we focus on part 1, where x coordinate matters. Among those, we wanted point A with biggest value x. And we have the same thing here. Among those points A, we want max of A dot x, and this is just that the x coordinate didn't change. We did something to be able to easily find points A that satisfy our two inequalities, and among those we want the best one. The best one is the one with biggest x, because we found points such that the distance by which we need to shift those points from A is equal to b dot x minus a dot x, because for them coordinate x was the worst one out of 3. And after I create this new drawing with a's and b's, I need to sweep from right to left, and when I meet b, what I ask is, just like previously, I ask segment 3, in this interval of values z prime here, what is the biggest value of x? And x isn't coordinate in this new drawing. It's value that we remember, because still point has that value x, and then we know this is a possible answer. By this amount we can shift such that there will be point A in the first out of 3 parts, that after the shift it will dominate B. And we need to repeat that 3 times for each coordinate. You shouldn't copy paste the code, just make a for loop that 3 times does something and then like rotates the coordinates. X, Y, Z should be switched to Y, Z, and X. And then for every point B, you will know, oh, from the first part, there is a point that I can shift by 5 to dominate B. From the second part, let's say I can shift something by 10. From the third part, I can shift something by 7. Then from those 3 values, you take minimum. Oh, I remember that from the first part, I could shift by 5. So this is the minimum out of 3. So 5 will be the answer for B. To make this point B dominated, I need to shift points A by 5. There's also the thing about max 0, this one, also in 3 dimensions. we just can apply it at the end. I can say that I remove it from here, I do that, and then at the end max of 0, comma, what I computed there, comma, the minimum over all A, and that will be also fine. Just possibly I will get number like -5. -5 is the minimum shift that B will still be dominated, and I can say this is 0 if the problem tells me that I only can shift by non-negative numbers. Or not to care about 0, you could first shift by -10 to 18, minus infinity, to make sure that no point from B is dominated. Are there any questions? I would say that the version for 70 points is a good simple data structure exercise plus sweep lines, while the version for 100 points is just hard to get observations, but in my opinion beautiful ones. The complexity that we have here at the end is just 3 times n log n for sorting by some coordinate, z prime and y prime, and using segment trees. We don't have binary search. For every point B, we just compute that minimum shift. And remember that all the coordinates, the y prime and z prime that we computed, by which we need to sort and also build segment tree over values z prime, this should be compressed, obviously, to interval 1n. At the beginning, sort everything, remove repetitions, and so the standard thing, if you have 10, 2, and 5, you need to change that into, say, 2, 0, and 1. I think we talked about this already. So whatever, doesn't matter. There is one more problem that is quite hard. And the funny thing about it is that we covered the technique needed for that yesterday, but even if you know this technique, this is just too hard to solve during the contest. I don't understand why the organizers used that problem at all. The solution, the intended solution, the one by organizers, has over 400 lines of code. I think maybe I would be able to code it during the contest, assuming that there was no other problems. But after solving other easier problems, you have at most maybe 2 hours for the last one, and it's close to impossible to solve it that quickly, especially for people from high school. And the last problem is, what is it? I will open it here. Yet another tree problem. There is a tree. Edges are weighted. They have weights or lengths. Some vertices of the tree are marked. The queries are mark the vertex and mark, change the weight of edge. After each operation, your program should output the maximum number x such that there is a simple path with at least 2 marked vertices on it with total weight equal to x. Okay, and there are some drawings that I cannot copy. I cannot. Let's see. Okay, so for example, for the right tree here, one of good paths is 3, 1, 2, 4, this one, because it contains at least 2 black vertices. We can unmark some vertex, so make it white or make it black, and the weights of edges change, plus they can be negative. What also wasn't necessary in this problem, it only makes it more complicated. My first thought after I read this problem was that I'm kind of looking for the diameter of a tree. this is yet another tree problem. Oh no, I forgot to put letters. This was D. We have a tree. Some vertices are marked. And my first thought was that if I look at the graph, the smallest possible graph that contains all marked vertices, I'm kind of looking for the diameter of this graph. I cannot have a path that is strictly outside of that. It actually needs to contain at least two marked vertices, not just one. But for the outside, for sure, for every direction, I just want to know the longest path that grows in this direction, and that's it. Then I can focus on the tree that is inside. This was one of my thoughts. And I remember that when so if the problem didn't have queries, then what we often do is bottom-up DP, that for every vertex it remembers the longest path down that has 0 marked vertices, 1 marked vertex, and at least 2, something like that, and then we combine. When we move to the parent, we combine among children, we choose 2 best ones and we combine them, something like that. It is possible to get this of n bottom-up DP, but it's very hard to apply it for queries that change the tree. There is at least one structure that allows us to make some updates and still modify the DP. And here I would think about either heavy light decomposition, what makes sense if paths are very important, or centroid decomposition. And then my next thought, still, this is not the intended solution. I'm telling you what I would try during the contest, and I think this would give us n times polylog, like maybe log cube, maybe log square, something like that. It wouldn't be easy, but you can implement it in 1 hour or 2 hours, not 5 hours and 500 lines of code. So after you find centroid decomposition, you can remember that and make some updates. So let's say there is some first centroid, the center of the tree. It has some children, each one with subtree. And when there is a change of some weight or some vertex marked to unmarked or the other way around, let's say this vertex changes, then what happens is that I want to update the DP values, DP of 0, 1, and 2 for this child. DP of 1 means the best path down that has 1 marked vertex. This should be doable because if I have that subtree of the child, so this is the child that I will focus on, it has some subtree, then the fact that something happens with this vertex, it changes paths that finish in the subtree of this vertex. Then maybe I can build a segment tree and I say for every vertex, 1, 2, 3, 4, 5, for every vertex inside, I compute initially the length of path that leads there, and I build a sequence over that after computing pre-order and post-order, like to change the tree into a sequence. And the fact that, let's say, this edge to some vertex changes weight, its length is now increased by 10, It means for everything that is in this subtree, increase your length from the root by 10. It will be for some interval of a sequence, increase by 10 after you represent tree as a sequence. We need to in some way care about the 0, 1 and 2 thing, and my guess is that we can do it with lazy propagation. That in this segment tree, every vertex of segment tree representing some interval, it will have values with 0 marked vertices, what is the best value, 1 marked vertex, what is the best value, second one, what is the best one, and then we lazily propagate something below, then this might shift. The issue here is, and I'm not sure if this can be resolved, as I said, this is not the intended solution, but something that looks reasonable to me, that after we are told by the parent that we get +1 here, then maybe we would need to, or -1, we would need to here use value that is the best thing for 3 marked vertices, but I think we don't have to. I didn't implement it, so as I said, I'm not sure. You can think about it later, just if it's impossible, yeah, maybe it is indeed. I think that is enough, and then we can merge 2 children to the parent, using, if the parent is marked, then we only use things like, if here we had 1 marked thing in the path, then here we will have 2 already. And yeah, lazily we don't propagate lazily the number of marked vertices. We just propagate the change of some weight. That, hey, for you, all the distances to you are now increased by 10. I hope so. And this will give us complexity n plus q times log, maybe square. For sure, log for centroid decomposition. When something changes, we need to change it on every layer of centroid decomposition. Every point is in each of up to log layers. It's in one of trees of one centroid for each of log layers. Times we use segment tree with lazy propagation. This is another log. So I hope that this is n plus q times log. You can investigate that. And now the intended solution that I'm sure it works. This is the one but organizers, but it's so not pleasant to implement. And this is to use the technique we talked about yesterday. Divide and conquer over queries. And this is, we have some tree, and there are queries. Query 1, 2, 3, 4, 5, 6, 7, 8. We split in the middle, and when we go recursively to resolve queries from 1 to 4, we first look at what these queries will change. Let's say they will change the state of this vertex, state of this vertex. Let's mark them blue. Blue denotes things that will change among those 4 queries. Let's say that those. Then for every edge, maybe to simplify things, I will just mark the 2 vertices that are connected with this edge as changed. And then I know everything outside of those marked vertices will not change. And I can compress it. For this part, I'm just interested in the best path that is there inside. Some vertex are marked here. So I want to know values, just best path that is there. And also in this direction, dp of 0, 1, and 2. The best path that grows from here, and it has 0 marked vertices, 1 marked vertex, or at least 2. And I know nothing here will change. Plus, there are some parts that are between blue important vertices that will change, and also I need to compress that. This part needs to be compressed to one like gadget box that says I can, between those two vertices, I have a path that has exactly that many marked vertices and its length is that. Plus also in this direction and in that direction, what is dp of 0, 1 and 2? Because maybe from that some other things grow. Maybe the optimal path will be, let's say, using that vertex and maybe this one, then it will go here. So I need here that dp of 0, 1 and 2. And here as well, dp. And the goal is to find those interesting vertices and compress the graph to be of size O of the number of interesting vertices. Likely you will have something like 2 times interesting or 3 times interesting, the gadgets, and you need to be smart about it. If there is very interesting vertex here and it has a lot of neighbors, you need to compress them into one thing. Just remember that there is a blue vertex and there is a path that grows out of this vertex. With the best one with 0 marked vertices has length 7, with 1 marked vertices it has length -2, and with 2 or more it has length 3, something like that. Actually this should be decreasing, but whatever. So for every blue vertex you remember that dp thing, the best path that grows outside. Then when you focus on those queries, you just have graph that has size O of the number of queries here. So you will resolve this part in complexity of 4, the size of this part times logs, log to something. And then the same, after you're done with the left part, then move to the right part, again compressing, and interesting vertices are only those that will be changed somewhere here. Any questions? The complexity that we'll get is n plus q times some logarithms, one from divide and conquer over queries, and the others for whatever we do inside. I won't be even surprised if we don't have any extra log. I think it is possible here to get n plus q times single log, maybe with a big constant, because from every vertex we'll know at least those 3 values, what is the best path that grows out of this vertex, but also between 2 interesting vertices we need to know something. In particular, we need to figure out what to do about this case, where those are interesting vertices, and here we have one white one, and then I think we shouldn't compress it at all. It's just that we want a tree that will have some blue vertices. I think those will be leaves of that tree. Maybe some of them will be connected with each other actually, so they aren't just leaves. And possibly they are connected, let's say like that, and that's fine. But then the thing is, if there are 2 white vertices or more, maybe 3 or more, and nothing blue grows out of the middle one, then you need to compress it. You need to remove the thing in the middle and say there is compressed path like this, and it has some values. Like you need to remember those 3 dp things. How did you get a log in complexity? Log is from divide and conquer. There are log layers of recursion. And maybe extra log will be helpful when dealing with compressing the thing, and maybe not, depending on whether you need some segment trees to compress the tree or not. It is possible to avoid it. Then the only log will be from divide and conquer on queries. Assuming that linearly you can compress the tree, you will have n plus q times log. I think we are done with problems A, B, C, D, E. Now we will get back to the C prime part, that is how to find the intersection of half planes. And also for that, maybe we'll talk a little bit about things like convex hull trick. So generally how to handle lines in terms of convex hulls. There is, by the way, a very good source to learn geometry. Topcoder, geometry tutorial. There is Topcoder tutorial that introduces you to geometry. If you don't know it, after this lecture, you should go through it. It talks about dot product, cross product, for example, line point distance, polygon area, given a polygon, not necessarily convex, how to compute its area with integers, with cross products. Then there is section 2 that is more complicated, and then section 3 that is even more complicated. In section 3 we have line-line intersection and line point distance, and examples maybe of non-trivial problems. I will not now cover basics unless you want me to. Tell me in the chat which one do you prefer. Do you want to talk now about basics, like what is cross product, how to use it, how to find, I don't know, convex hull of points? Or should we move just to the hard part, that is dealing with lines and then half planes intersection? I will give you the link for that. And I will put it later in the Google Sheet. We will quickly talk about convex hull trick. I will not explain the whole thing. Instead, I guess only me is not familiar with geometry, but I will probably be able to catch up after the lecture. Yeah, so then read the Topcoder tutorial after the lesson, after the lecture. First, about convex hull trick. Again, I assume that most of you know it. If not, tell me in the chat. We'll talk about similarities of it with convex hull and half planes intersection. Each of you knows how to compute the convex hull of points. And for that, we either sort by angle or by x-coordinate. I assume that by, let's say, x-coordinate. And the implementation is if we have some points already in the stack and we have a new point, then it might, this was already convex hull, then the new point might pop some previous point because it was below the new point. This is new stack. The implementation, it's not that I now teach you the standard convex hull of points. I want to show you similarities with half planes intersection. I need this with different font, consoles. I can type here. So it's something like for every point P in points, sorted points. Why is the font size changed? Well, something. Do I need to change font size every time? That's stupid. What do we have? A is whole of second last element, B is whole of last element. If OC of A, B, C, then I will increase the font size in a moment. Then whole push back C, P, break, else will pop back. We will work with this code. Is it okay? Yeah. Here we need condition like while the whole size I think is at least 2. And I think we're good. And this will compute the upper convex hull. The function awk of 3 points a, b, p checks if they are in good relation to each other. That is a, b, and let's call actually that third point c, because then it's easier. So every new point c, we check if it's good relatively to a and b, if everything is convex. If b is below the line AC, A, B, and C, then this is bad. We don't want that to happen. Yeah, so awk changes if we have the scenario that is above. And the cool thing is this works for the code that we have here. Maybe I will change this the name here to objects. It works also for lines. It also works for half planes. This is universal. It's just that the function awk will change. The implementation of this function will be different. What happens for lines? How to move it? What happens for lines? If I have, let's say, functions like y is equal ax plus b, and I need to use convex hull trick, that is, let's say every line gives me, every line describes some taxi company. The taxi company charges you $B for the start of the trip, and then $8 for every next mile or kilometer. Then if there is x, then the y here denotes price. Every taxi company can be described by a line like that. And for some, there are queries for some x, which taxi company will be cheapest. Maybe if x will be small, then likely you want to choose something with small b, the charge for the start. And if x is huge, then eventually you want the one with smallest a, price per kilometer. The solution is to sort lines by slope, so that in that optimal, there will be some lines that are optimal, and they are sorted like that. So it looks generally like that. This will be description of optimal taxi lines. Some will be skipped. Even in the drawing above, we see one taxi company that is never optimal. We should find this line of the lower convex hull, something like this, and then for given x we can, let's say, binary search which of those lines is best, and here we sort by slope like that, and then just apply the code on the right. If we have some stack already, and now a new line comes, if it's like that, then we compare it with two last lines and we check if one of them is covered. If it's like that, then one of lines is covered. Let's use a bigger drawing for that. And assume that the A value can be negative, but it doesn't matter. If this was A, this is B, and this is C, then the function OK should return true. Each of those three taxi companies can be optimal for some x. They belong to convex hull. But if C is here, A and C together, they dominate B. And this is forbidden, this is not okay. And it corresponds to the thing I drew on the left for 3 points, A, B, and C, that B is covered. It's never better than A or C. A and C together, they cover B. And just the implementation is slightly different. So what we should do for, what is the function OK for different things? For 3 points, A, B, and C, the easiest thing we should do is to compare, to check the cross product of vectors AB and AC. For 3 taxi companies that are sorted by slope, this is A, this is B, and this is C. I usually do the following. I actually just copy the implementation that I have on my computer, but you should be able to figure out that yourself. In problem with taxi companies, I have function that, let's say it does get intersection X of 2 lines, let's say A and B, and this should give me X coordinate of this point, then also X coordinate of the intersection of B and C, and I will compare those two. So for 2 lines that are each described by that, by 2 constants A and B, to find their intersection, one is described by this equation, the other is described by this equation. Then you need to just compare the 2 things and say those must be equal. So for this X, the Y's coincide, they are equal. And get X from here. X is equal B2 minus B1 over A1 minus A2. We have here division by 0, but only if 2 lines are parallel, the slope is equal. This gives me this X, let's call it X1. Also, I will compute X2. And function OK checks if X1 is smaller than X2. Then they are like that. If in the wrong order, A, B, and then C, those X1 and X2 are in the other direction, because B is here above intersection of A and C. So then X1 would be here and X2 would be on the left. And if possible, try avoiding real values. I already said that in one problem today, and it's easy to do because we want to compare this. This is X1. We want to check if this is smaller, question mark, is it smaller or not, with something like the X2 is intersection of what, let's say B and C. So it will be B3 minus B2. B3 and A3 describe the third line over A2 minus A3. And you can check this inequality with integers only, because you just multiply 2 sides by what is below. You check if B2 minus B1 times A2 minus A3 is smaller than B3 minus B2 times A1 minus A2. One thing you need to be careful about is the following. If you have A over B is smaller than C, you can multiply 2 sides by B only if B is positive. You can say that from this you get that, but only if B is positive. Otherwise you need to change the side of inequality. But we are lucky, if we already sorted lines by slope, we needed to do that to apply the convex hull, then this thing is positive. The first line has bigger slope than the next one, and this is also positive. that's how you, with integers, find the convex hull of lines of form ax plus b. If you have any questions, of course, ask them at any moment. Now, this works if we only want one side of the convex hull. Just like with points, it's a bit easier to find upper convex hull, just going from left to right. If we need to also go with the convex hull below, we would need to kind of repeat that below, do something like that, and it makes half-planes intersection a bit harder. So the difference between those functions ax plus b and half-planes intersection is that half-planes intersection have directions. Each line, we are given a bunch of lines, and also each of them has a side. You can think about them as, let's say, directed lines. The drawing from the left I will represent as vector like that, and like that. For each of them, I know that the area to the right from him is it is allowed. Let's say if we have also that, then I have here this vector. And now what we do? So this vector is described by the starting point, which means where this line is, and the direction. Sorry, don't we need to compare x intersections of lines AB and AC? Here it doesn't matter. What happens is, what I did is I looked at line B, and I wanted to know which of those 2 points is more to the left. What you wanted to do is you wanted to see at line A and compare the x-coordinate of this point and this one. Your method and my method are both correct. Similarly, for version with points, ABC, also we could compare vector AB with BC instead of AB with AC. That will also give you correct thing. Whatever is more intuitive for you. How to do half-planes intersection? We should split the lines into those. We now have vectors. Let's split vectors into 2 parts. Those that go to the right, like that, and those that go to the left. This way, the set of those things that go to the right, those represent half-planes that limit us from above. With those, we will compute the upper convex hull. And so the goal is, let's say, if we have those lines, then we just want to get rid of those unnecessary ones, and we will have in the order the good shape, the convex hull. This is area limited by the upper lines here. And we do the same thing that we did previously, just that intersection will be a bit harder to compute. We sort by slope, and in this order we check for 3 consecutive lines with this code to the right, and just function OK. Again, it will compare 3 intersection points. But also we need the below part, and at the end we need to combine them. And this is not that trivial, because maybe if, let's say, with white I will mark the upper part, and now the shape that we have is that, the area that we have. And now with blue I will mark the part below, let's say it's that. This represents this area, and then the combination of the upper part and the bottom part should be just this part. So the upper part and part below, they might together remove some stuff. So after you compute the, let's say, upper 1, upper 2, and upper 3, of course there can be linearly of many of them, and then below 1, below 2, then you need to check. Imagine that this is on a circle. Upper 1, upper 2, upper 3, then below 1, below 2, and so on. Then maybe upper 3 will be removed by together upper 2 and below 1. It's a similar thing with, like, convex whole thing is easier because nothing is removed. So it's harder for half planes. This is one difference between the two. So we will modify the code a little bit for half planes. This is now just half planes intersection. Let's say that objects contain all the points, not split into upper and below part, just all the points, all the lines, sorry, sorted by slope, whole 360. And then at the end, we do the following. While not awk of hull of -2, hull of -1, and hull of 0, hull pop back, and while not awk of hull of -1, hull of 0, hull of 1, hull dot erase 0. Bigger font, please. I didn't want that. Okay, it more or less works. The thing is, for half planes, the whole drawing is symmetrical. I mean, if we rotate everything by 20 degrees, let's say, nothing should change. The same lines are, they limit the area inside. There isn't any magical difference between lines above and below. So we should just think that they are in a circle. 1, 2, 3, 4, like limiting those areas. And maybe the last of upper ones, they will remove together with the first of bottom ones. Maybe there is a scenario like that, and this will remove the bottom one. So here we treat everything as a line, like starting from the first line, then we add every next one to the stack, but then at the end also we need to remember that this is a circle, not a line. That the end is kind of connected to the beginning. And here -2 denotes the second last element, -1 the last element, and we check basically for every 3 consecutive elements for our circle, we want to check if the one in the middle is not okay. It's covered by the other 2. If yes, we pop back. And this is pseudocode. We cannot erase 0. I mean, we can, but this would be linear. Here in actual code, to check, you need to check how many first elements you erase. And for that, I would just store a pointer that points to the beginning, or have that as a queue or a list that is able to remove from the start or the end. The vector is fine, just with extra variable that will tell us where is the start. Plus those 2 might, after we remove the first element a few times, then maybe the new first element will cover the last one. So the code should be more like, while anything happens, if not awk of -2 -1 0, then erase of the last element. If not awk of -1, 0, 1, erase of the 0th element. And that's the correct code. Plus, remember that half-plane's intersection can be empty. In particular, you need to check here whether maybe the size of hole becomes smaller than 3. This would mean that, is it empty necessary? It's not. If size is now 2, something like that is possible. Either this is the scenario already, or yeah, this is the only scenario if half planes aren't parallel. For 2 parallel ones, this is possible, or even then and then this is the area, or they can look at opposite sides. Then the intersection is empty. You need ifs for that, if 2 half planes can be parallel. And when we compared the x-coordinate, we used the fact that things go from left to right. And we need something better now, and that is actually what we need is that for 3 lines A, B, and C, we need to actually check if along the line B, the 2 intersections, the one with line A and the one with line C, they are in good order. If B goes in this direction, so it limits the area to the right of this vector, then we can take, let's say, intersection point with A, intersection point with C, and check if this vector from the first one to the second one is the same as the vector of B. Or we can check if dot product is positive. That's one possibility. But the other, much more standard approach is that if every line you describe as ax plus by plus c is equal to 0, then for 3 lines A, B, and C, so this was A1, B1, C1, if you take the coordinates A1, B1, C1, then A2, B2, C2, A3, B3, C3, you need to compute the determinant of this matrix, which is A1, B2, C3 plus B1, C2, A3 plus C1, A2, B3 minus the other diagonals. This is determinant. I hope I spelled that correctly. Determinant of matrix. We did the same thing actually in 2 dimensions. Here, checking that, this is exactly determinant of matrix. Of what matrix? Of 2-dimensional matrix that has vectors from A to B and from... Oh no, we have 3 lines. What do we have here? Maybe it's not that trivial. But here, when we have 2 dimensions, to checking the cross product of vectors AB and CA is exactly computing determinant of some 2 by 2 matrix, because cross product is determinant of such a matrix. So there is some similarity between this case and the harder one with half planes. So what I do during contests is I implement this thing, and you can either think about whether you want that to be positive or negative, or just type some example or like run it for sample test and choose the one that will work if you don't feel confident in understanding what happens. If determinant is positive, then return true that yeah, those 3 lines are okay, otherwise not. By the way, if 3 lines intersect in the same point, determinant will be 0. And also with those inequalities that you would compute from intersections, you would get equality. Time for questions. The complexity of this is n log n for sorting plus O of n. And if things are already sorted, and that was the case in problem C, then the complexity is linear, just like convex hull of points. Just remember here, you don't erase the 0 thing explicitly, because then vector would shift by 1 and that would be linear per every erase. Instead, have a pointer to the start, or the int that says how many first elements are erased. If that int is 3, and you need to check with the 0th element, then you check for hull of 3. Can OK function be like take vector product between line and intersection point? Yes, it can be. There are a lot of ways. In geometry there are a lot of ways, but here the determinant is safest, easiest. And also, if you already have this form, then you have just integers. That being said, here you would need to get this form. What the intended solution does, I saw the code, is that every line in problem C, every line is changed into this form A, B, and C first. And they change that to doubles. Most of the time it's possible to get some big numbers that are still integers, but here they change that to doubles, to real values. But yeah, if you figure out some other method, like say for 3 lines A, B, and C, compute the intersection of A and B, and then check if it's on the right from vector C, this is also fine. And you will get slightly different formulas, but if you rearrange the elements in those formulas, you will get the same thing. All the methods will actually check the same thing. Just remember that if functions are of easier form, ax plus b, like with taxi companies, then it's easier to just compute the intersection with this ratio, the fractional, and then transform it to make the check that is here, which is just like determinant. But it will take you 1 minute to figure out the exact formula. You don't have to switch the format of a line into the form ax plus by plus c is equal 0. My implementation sometimes here is, instead of awk, I say something like if is below or covert A, B, C, then I pop back this B, and otherwise I break, and then do pushback. One more detail. Because you have that, if the size became smaller than 2, you still want to push back the C. So it's better to move this here. Every next line you want to once push back. That is better. Now we are good. I'm saying you can switch this to if is covered, so not okay, then hull pop back, else break. In C++, by the way, you can write this. And that is now not pseudocode. This works. A and B will be second last object and last object. Of course, last object can also be accessed like that. But maybe this looks nicer and we see what happens. Also, in those ifs there, you can use this thing for accessing the second last element.